In this video, we're going to finish up Chapter 2 and work 2 example problems. One example problem is going to be finding equivalent conductance, and the other one we're going to do is a delta-Y conversion problem. So sometimes it's easier to work with conductance instead of resistance. So the problem I'm going to do is problem 211, which says to find equivalent conductance. So first, recall that Recall that for resistance, R total or R equivalent for resistors in series is the sum of the resistors. For series. And for parallel resistors, it's 1 over R, I'll say equivalent this time, equals the sum of 1 over the resistances, which is 1 over R1 plus R2 plus ... So this is for resistors in parallel. So remember that. Now, when we deal with conductances instead, it's kind of flipped. So for series, and if you're dealing with conductance, 1 over G equivalent is the sum of 1 over the conductances, because conductance equals 1 over resistance. And for parallel, conductance total is the sum of the conductances. So if this problem, everything is given to you in conductance instead of resistance. I could go over here and say, well, the resistance is 1/8, the resistance is 1/4, resistance is 1/2, etc., and work it with these equations up here, or I could just use the fact that they've given everything in conductance and work the problem that way, which is really the intention of this problem. So that's what we're going to do. So if I look at this problem, what I actually see is that these two resistors with their conductance written are in parallel, and these two are in series, which is in parallel with that. So convince yourself, just for the fun of it, that the problem that I really have here looks like this. No reason why I can't write it this way. Sometimes people see it better that way. No reason why I can't write it that way. These two are in series with each other, and this is in parallel with these two that are in series, and this way I'm clearly separating out the two parallel sections. Sometimes when people see a line, a short between the resistors like that, it's confusing. So anyway, resistances in parallel, if you're given it in conductance equivalent for this pair over here is just add them up. It's 8 plus 4 Siemens, which is 12 Siemens. So this part down here, so that's that part. This part down here, it's 1 over G equivalent is 1 over 12 plus 1 over 6, and then you do the algebra and you'll get the answer to being 4. The shortcut math, if you don't want to do all these 1 over things, is G equivalent equals 12 times 6 over 12 plus 6. So that's the math shortcut, which works with 2 elements only. So we have this one, and that's in parallel with this resistor. So I'm going to redraw for a moment. We have 12 from the first equivalent conductance, and over here right now we have a 4, and it's in parallel with that 2. So that's where the circuit's at right now. So we have these two in parallel, which is a bit trivial. That in the math anyway, that becomes 6 Siemens. This one is 12 Siemens. So that's our circuit right now. So the last thing we have to do is find G equivalent, which is the conductivity you would measure between these 2 points in the circuit. And in this case, G equivalent, because these are in series. So it's a formula like this, would be 12 times 6 over 12 plus 6 again, and the answer is 4 Siemens. So this circuit with all of these resistors ultimately in the end can be replaced with one equivalent resistance or one equivalent conductance, where the equivalent conductance is 4 Siemens. Of course, that corresponds to the equivalent resistance of being 1/4 ohms. This problem is pretty easy to find the equivalent resistance or the equivalent conductance just applying the rules for series and parallel. However, circuits such as this, you cannot find the equivalent resistance or of the circuit, or conductance as the case may be. So none of these resistors are either in series or in parallel right now, not a one, so you cannot simplify the circuit. However, what you can do is do a delta to Y conversion or a Y to delta conversion. Book says that you can pick 3 resistors in there and do a conversion, any one of the Y's or deltas, and then the circuit will be simplifiable. So book also says that there are 2 Y networks and 3 delta networks. I'm on page 56 of your book. But I find, so I'm going to point them out to you. So Y networks, also called T networks, I see 2 of them. I see 3 of, no, I see 2 of them. This is a T right here. Did I just say that opposite? This is a T right here. Okay, maybe there are 2 Y networks. I am corrected. There are 2 Y networks. There's a Y network. There's a Y network. I do not see another Y network. So let's look at the T networks. Y and T are the same. Let's look at the pi networks. So pi networks. Pi networks. This is a pi network. Oh, sorry. This is a pi network right here. This is a pi network right here. And then there's one more pi network. This one right here. With these 3 resistors. This is also a pi network. So I could curve this around and make this into a triangle shape, which would be a delta. Pi or delta, they're the same thing. Okay, so there are indeed, sorry I said it wrong, there are indeed 3 pi networks, also called delta networks, and there are 2 T or Y networks. So I can pick any one of these that I want and convert it, and then the circuit should be simplifiable. So let's get rid of that real quick. So I'm going to pick any one of the pi's or any one of the deltas, and I'm going to convert it to the other circuit, and then the circuit should be simplifiable. So the one I'm actually going to pick, I'm going to pick this T network, also called the Y network, and I'm going to convert it to a delta network. So I'm going to draw the delta network in that I want to convert to. I'm going to draw it in. It's going to be a resistor right there, and then a resistor right here, and then a resistor right there. So that's the network I'm going to convert. So these resistors will go away. I'll put in new equivalent resistors there, and then the circuit should be simplifiable. So the next thing to do is just careful accounting and applying your formulas here. So if I call this resistor, I'll change my color so it shows up better. If I call this 10 ohm resistor R1, I call this 20 ohm resistor R2, and I call this 5 ohm resistor, I'll call that one R3. And then I have to go over and label the equivalent resistors that I'm going to convert to. So a little bit of the trick is, if this is R1, then the RA has to be opposite on the triangle over here. So if this one was R1, then this one should be RA. So this is where you have to think carefully about the circuit. Actually, I should redraw it so you can see it better. So let me redraw it better. So I'm just going to draw it from point A to point B. I still have the 12.5, and I still have the 15 ohm resistor there, and so that you can see a little bit better, this is the 5 ohm resistor. And if you want it to look like a Y, this is the 5 ohm resistor. And then I'm going to change this angle of that 10 ohm resistor and bring it up here, 10 ohm resistor. And I'm going to change that angle of that 20 ohm resistor, R2, and I'm going to bring it out here. So now it looks more like a Y. This is the original circuit. And then the original circuit also has a 30 ohm resistor out here. So this looks more like the original circuit, and then if I want to go in and do my conversion, the circuit that I'm going to convert to is right here. This one, and this one. So this is what I'm going to convert to. So this is R1, R2, R3, and then labeling the other resistors, the blue resistors, the new network. So this is the 10 ohm resistor right here. So across from the 10 ohm resistor has to be RA. Across from R1 has to be RA. Across from R2 has to be RB. And across from R3 has to be RC. So you have to be able to visualize what's really happening in the circuit, and sometimes it helps to redraw it, which is what I just did, is to redraw it. So so now we'll go ahead and do apply the formulas. So if you apply the formulas, because we are going to convert a Y network, also called a T network, to a delta network, also called a pi network. So that's the conversion that we want to do. At this point now, we've carefully set up labeling of the resistors so we can apply the formula. RA equals R1, R2 plus R2, R3 plus R1, R3 over, so it's the opposite resistor there. Well, RA, we're finding RA, and it's the opposite resistor, so it will be over R1. And so you put the numbers in, the R1, R2, R3 numbers, and you'll come up with 350 over 10, which will be 35 ohms. So we found RA. Using similar formulas, we find out that RB is 17.5 ohms and RC is 70 ohms. So now if I redraw the circuit, I've done one conversion right here. I redraw the circuit. I have my 12.5 ohms. I have my 15 ohms. And then I have this new circuit in here, which right now looks like this, this, and this. And then I have the 30 ohm out here. So maybe you're not quite visualizing it yet, so I can redraw it a little bit more. Let's see, let me put my numbers in so I don't lose track. This one is a 17.5. This one is RA. RA is 35 ohms. And RC is 70 ohms. So I'm going to redraw it one more time. Plus minus. Like I said, it's hard to look at the monitor and draw somewhere else. 12.5, 15, and instead of having my node come together and go at weird angles like that, I'm actually going to do like this. There's my 17.5 ohms. So I just extended this into like a straight line. And then there's my 35 ohms. And now I also have a 70 ohm and a 30 ohm. Let's see if I can go to the next slide with that. So we'll finish up this one example here. Select objects. Copy that. So there's my circuit continuing. So on the circuit now, I see that 70 is in parallel with 30 ohm resistor. So 70 in parallel with 30 equals 70 times 30 over 70 plus 30, which will equal 21 ohms. I see that 12.5 is in parallel, 12.5 is in parallel with 17 ohms. And so if I do 17.5 ohms, so if I do that calculation, I will get 7.292 ohms. And down here I see that 15 is in parallel with 35 ohms. So the 15 in parallel with 35 will give me 10.5 ohms. If I redraw that circuit one more time just to keep track of it, I now have a 7.292. I have a 10.5 ohms. Then I have a 21 ohms. So I convert this series. I can convert that into a series, which is 17.792 ohms. So the last thing I have to get an equivalent resistance then is, there's my R equivalent, will finally equal the 17.792 in parallel with 21 ohms. And you will find that the equivalent resistance is now 12.4, no, it's sorry, 9.632 ohms. So that's between point A and B. So I think your book calls that RAB. So resistance between A and B is 9.632 ohms. And then I think it asks you to find originally what this current is in the circuit. So just using Ohm's law, current equals voltage times resistance between A and B. So it was 120 volts. divided by 9.632 ohms, and you end up with 12.458 amps. Answer, answer. So that's how you can actually analyze this circuit when none of the resistors were purely in series or purely in parallel with each other.